pre-university studies at Asasi Science, University Malaya in 1994. He completed his first degree and the Masters of Engineering Science in Electrical Engineering from the University of Malaya in 1999 and 2003, respectively. Subsequently, in April 2009, he obtained his PhD from the University of Manchester with a specialization in electrical power systems. Prof. Hazlie's career in started in 2003 as a lecturer after completing his master's degree under UM's Academic Staff Training Program. Since then, we are honored that he has dedicated his life as a academician. With strong support given by in teaching and research activities, his career has progressed very well since then, and he was promoted to senior lecturer position in June 2009, an associate professor in January 2013, and as a full professor in July of 2016. He is indeed a very dedicated educator and has actively supervised numerous students at all levels of studies, bachelor, master's, and PhD. His impressive track record includes 27 PhDs, 7 Masters of Engineering Science, and more than 50 master's projects that have been completed under his supervision and co-supervision. And currently, there are 20 PhDs and 3 Mechanical Engineering Science active students currently under his supervision. So I don't know, your family, I really congratulate you for supporting such an effort by Prof. Hazlie. His area of expertise is in electrical power system, focusing on improving the performance of electrical distribution systems through the application of various optimization techniques. His research includes detection of fault location, network reconfiguration and restoration, power system quality, as well as islanding operation of the network. Currently, Prof. Hazlie's research mainly focuses on power systems resilience, which is also the topic that he will talk in great detail today. Prof. Hazlie's work has raised close to 2.5 million ringgit in research funding as principal investigator in the last 5 years. Additionally, he is also head of the Power and Energy Research Group, whose main focus is in carrying out work on the latest high-impact research in power systems area. The group has collaborated with both local and international universities, including UNITEN, UTM, UniKL, UTEM, UITM, University of Manchester in the UK, National Cheng Kung University of Taiwan, Brawijaya Indonesia University, Sao Paulo State University Brazil, and UEA University in the Middle East. To date, he has published his research findings in more than 300 academic papers in journals and proceedings. The quality of his work is reflected in the number of citations that the papers have received, both in the Web of Science, more than 2,700 citations, as well as in the Scopus database with more than 3,000 citations. In the past, Prof. Hazlie has held multiple important management positions, starting as the program coordinator in 2011 for E&E program. From January 2014 until August 2019, he has held various top management faculty positions: Deputy Dean of Research, Deputy Dean of Higher Degree, Head of Department, and his last post was as Deputy Dean of Undergraduates. During his tenure as Deputy Dean of Research, he has led the faculty in managing the high-impact research grants, where the faculty successfully fulfilled its overall KPI set by the university. As the Deputy Dean of Higher Degree, the faculty always managed to fulfill the KPI on the number of PhD students graduated. And as the HOD, he has led the department in improving various critical aspects in terms of facilities, student and supporting staff empowerment, mentoring scheme, and systematic department management. In addition, he has initiated a few engagement programs between the department and the industries that include activities such as industrial talks and visits, scholarship opportunities, industry attachment, sponsorship from industries to develop student study areas, as well as industrial grants. For sure, all these successes cannot be achieved without strong support given by the faculty management, colleagues, supporting staff, and of course, family. Currently, he is serving as a University Senate member representing his faculty. Internationally, Prof. Hazlie serves as a visiting professor at the University of Brawijaya, Indonesia, and UEA University. He has served as keynote speaker at various conferences and as PhD external examiner at multiple international universities. He is also an active reviewer for several high-impact journals in the area of power energy systems, assessor for academic promotion, and evaluator for research grants. In Malaysia, he is no less recognized. He was part of the evaluation committee for the selection of high COE, LRGS and TRGS grants at the ministries. He has also been involved as a member of the committee for improving teaching modules for Malaysian for the He has been appointed by the Board of Engineers Malaysia as a panel evaluator for Engineering Accreditation Council. Prof. Hazlie has also actively contributed to societies. He is an active volunteer for IEEE Malaysia section, where he has been an IEEE Power and Energy Society Malaysia Chapter Executive Committee member for the past 3 years. Currently, he is also Vice Chair for IEEE PS Chapter, Malaysia Chapter. Prof. Hazlie was involved in 2 working groups under SIRIM, which were responsible for establishing 2 important Malaysian standards. 1, Studies and High Voltage Switchgear Control Gear and Assemblies, and 2, Guidelines for Power System Steady State, Transient Stability and Reliability Studies. At the international level, he is the expert representative in IEC for TC8/PT. No, I'm just reading this part because this is heavy engineering for me. 62786 project. At the community level, Prof. Hazlie is the committee member of his residential area, so he has time also to contribute to his community. Prof. Hazlie is a professional engineer in Malaysia, a chartered engineer in the United Kingdom, and an IEEE senior member. So with that very brief introduction, and I believe there's so much more that Prof. Hazlie will share with us, without further ado, I would like to invite Professor Engineer Dr. Hazlie Mokhlis to present his lecture entitled Power Systems Resilience, Overview and Way Forward.
Thank you, Profina, for your kind introduction about me. I'm really honored to have you as chairing this session today. Thank you also to Dr. Anisalwa for accepting my invitation to be MC today. It's really great honor for me. Thank you to the event committee today, led by Puan Mohaini, which has did a very good job. The setting is very excellent and make me more nervous today because of the setting, which is very formal today. Not forget to the team from JPPHB, the team from PTM, and also Keselamatan for making sure that this program goes well today. It's a really big contribution from everybody. Thank you very much. Assalamualaikum and very good morning to distinguished guests, fellow colleagues from my department, electrical, and other department as well, researchers, students, and my friends, professors, lecturers from various universities. Today I can see from APU, UKM, UTEM, come long way from Malacca. Thank you very much. Uniten, UCSI, Teller, MSU, UITM as well, and also Tengku Abdul Rahman College University. And they're also from industry, ILSAS and TMB. It's really great honor for me, and I'm really delightful and touched with your support to me today. And ucapan terima kasih juga untuk my family member, untuk keluarga saya. Ibu saya ada bersama, isteri saya, 3 orang anak saya, 2 orang lelaki tu. Saya ada 6 orang anak, so dapat bawa 3 orang yang lain sibuk dengan urusan belajar. Walaupun mereka mungkin tak faham my presentation today, but actually the attendance is very meaningful to me. And to be frank, actually I'm really nervous today. However, I will try my best to present the topic about resilience, power system resilience. Before I begin my topic, this is the books that I have prepared for this inaugural lecture. However, this time we make it an e-book. Okay, so whoever interested to read detail, you can scan and you can download the books. All right. To start off, this is my outline presentation today. I will start with giving the overview of power system so that it will be benefited to everybody which is not in the power system area. And then I will discuss a little bit on the data of extreme weather around the world as well as in Malaysia data. Then I will talk about resilience, the concept of resilience perspective from the perspective of power system. And I will focus more on the microgrids because microgrids has been identified as the best option to improve the resilience of power system. Few example of research I conducted with my team in I also will discuss some way forward in the research, the ideas. I can share with you what is the other things that can be done to improve resilience in power system. And then concluding remark, and I will also acknowledge important person in my life. Yeah? All right, so as a start, let's see what is a power system. Just a revision. Okay, so basically power system is a system to deliver electrical from the generation to the customer. In general, that is a power system. Traditionally, power system start from the generation plant. Okay, traditionally from generation plant, it can be a diesel, it can be coal type, it can be biodiesel or hydro. Then the power that being generated from the generation station will be transmitted through a long transmission line. In order to do that, the voltage level need to be increased to 500 volt, 132 kV or 25 kV. And the highest voltage in the world now is 1100 kV in China. Because in China, the distance is too long. Because they generate a lot of electricity from hydro, and the hydro is at the mountain area. It's far from the people. And then the power that been transmitted will be distributed to the distribution system to the end customer according to their voltage level needs. It can be 33 kV, 11 kV, or like at our home, 230 voltage. Has changed because of the renewable energy, where the renewable energy is generated and connected at the distribution level. So there is more challenge. Let's see why electrical power system is very important to us today. Number one, because I believe that everyone agree that electrical is so important because it is needed for various sectors. For example, it is needed for banking sector, it's needed for healthcare sector, it's needed for agricultural area or food processing. Lot of area sector required electrical power supply. And furthermore, electrical power supply also, the system also interdependent with other sector as well. Okay, for example, like communication, because nowadays power system not only generating electricity, but it also use a lot of communication devices to transmit the data, to monitor the data. So it depending. I mean, it is not one way, but electrical power system also require the communication sector to support them. And also, like, we also need the gas supply to support the power plant so that it will generate power. And it also related to transportation, and also it related to communication for switching. Because the modern power system nowadays, they involve a lot of digitalization, all online. No need to go to the substation. It can be done, the switching can be done at the control center. Okay, so let's see why this power system is so important and why it is having problem when there are extreme weather. Yeah? So this is a very obvious event that recently happened in our life. We can see there are a lot of thunderstorm, we can see there are a lot of wildfire, and this is a lot of flood that happening around the world. This photo is in Kota Baru, Pengkalan Cepa near Kota Baru, where in 2014 there was a major flood. And this caused a huge losses, not only to the people, but also impacting the electrical power supply. And all of these events, we refer as low probability, high impact events. In power system, we call it low probability to happen, but the impact is so huge. Not only it will cause a lot of problem when this happen. And if you look at the pattern around the world, this data was taken 2018, okay, from Germany, this data. If you look at the around the world, there were a lot of catastrophic events happening around the world. And the event we can see can be divided into 4 categories. It can be geophysics, meteorological, hydrological, and climatological. It's depending on the event. For example, if you look at the Malaysia, we almost cannot see the map because there are a lot of event there, hydrological event, which is a flood. And in US, the major problem for them mainly is due to the storm. A lot of storm happen in US. And furthermore, if you look at the trend of the data, we'll see that the trend from 2018, from 1980 to 2018, we can see that the trend is keep increasing, meaning the extreme weather happening around the world is increasing, and we can see that the hydrological event, which is like the flood, is also increasing. So this shows that the impact of extreme weather need to be considered in power system infrastructure. If you look at the number of losses in terms of fatalities, we can see that more than 1 million people have been impacted by this extreme weather, and the losses is quite huge, for 4,200 billion of losses due to this extreme weather. This is in general. If you look at the impact of power system, this is some of the event that happened in the past years due to the extreme weather. For example, like in China, 2008 alone, 14.66 million households were affected due to the snowstorm. Fukushima, due to earthquake and tsunami, 4 nuclear reactors fell down because of the very strong wind. This is in China, 135,000 people affected. And the most recent outages due to the extreme weather is shown here. For example, in 2019 here, if we take United Kingdom, for example, this is the largest outage in the past 11 years in United Kingdom. And the people affected, 1.1 million people were affected without electricity. This shows how the weather can cause problem. And interestingly, in this event, what happened actually, there was a lightning strike at the transmission tower at the north of London. And this lightning strike caused tripping at the Bedfordshire power plant, which is located 100 miles from the lightning strike. As a result, at the same time, the Hornsea offshore wind farm at the Yorkshire, it become deloaded, meaning the power that being generated is reduced significantly. As a result, what happened, there was an unbalance between generation and demand. When this happened, the frequency is dropping from 50 Hz to 48 Hz. As a result, many others power plants, small power plant, they see that this is like loss of main grid. When this happens, it will trip off many of the power plant. As a result, a large outage happened in this area in England and Wales. So you can see that due to a lightning strike. So this is showing how important is that we need to consider extreme weather in designing power system network. And this is other example that happening around the world to show how severe is the impact of extreme weather to us. This data from US, 2014, 2018, we can see that the outages due to severe weather, it is very huge. 39% outages of electricity was due to extreme weather. Most probably in US, it is a thunderstorm. Okay. And this is a Malaysian data. If you look at 2013, 2017, we can see that the trend of flood that happened in our country is increasing. And the major problem when this happens in Malaysia is that it will submerge the substation. For example, if you look at 4 December 2013, this is the number of substations need to be switched off to avoid problems or to ensure safety of the people. So it need to be switched off. And the number of customers affected is more than 6,000. So this is how serious is extreme weather can cause problem to power system area. Okay, so let's start with the resilience. So the concept of resilience actually was started by an ecologist with the name of C.S. Holling, where he defined resilience as a measure of the persistence of system and of their ability to absorb change and disturbance and still maintain the same relationship between population or state variables. So here, the keyword here, if you look, it should be able to absorb change and disturbance, and it should able to maintain the same relationship, mean it should be continuous working. So this is from the ecologist point of view. Okay, and from different organizations, at the moment there is no standard definition of resilience from the perspective of power system. Different organizations, they have their own standard or their own features of resilience. This one I took from National Infrastructure Advisory Council, US, and Cabinet Office, UK, where this is the features they define. It should be robust, resourcefulness, rapid recovery, and adaptability. This is the concept of resilience from this NIAC. And other organizations actually, they have their own definition of resilience or characteristic of resilience from different organizations. This is like from the earthquake engineering research. So this one is more towards civil engineering actually. Yeah? And others is from UK and US. If you look at the resilience from the perspective of power system, the closest is from UK Energy Research Center, where they talk about energy services. Yeah? At the moment, there is no standard, so we can say that the goal of resilience in power system is to predict before it happens, withstand when it happens, bounce back, and adapt to unprecedented disruption. Because as we know from at the beginning in my talk, we have seen that low probability, high impact. Mean the probability to happen is very low, but the consequence is very high. So the system should be able to anticipate before it happens. Yeah? So in general, I can summarize that resilience, in summary, it should have this characteristic: withstand, lessen and adapt, anticipate, minimize impact, absorb impact, handle uncertainty, isolate healthy section. In order to understand the concept of resilience in a power system, maybe it's good if we look at this resilient curve. It will give better understanding, the concept of resilience. All right, so the y-axis here representing the function, system functionality, and we assume at this point it's 100% function, and this is the time, the y-axis, the time. So before anything happen, during normal condition, the system should be able to anticipate and prepare. I mean, it should be prepared before extreme weather happen, it should be prepared. I mean, it should be proper planning when it happen, what should be done. This is the original operation state, 100%. When disruption happen due to extreme weather, we'll see that the functionality of the system will degrade. It will degrade. But the rate of degradation should be slower. It should be slow. So if you compare with the traditional performance here, the rate 1, you can see the rate of degradation is slowing because the system should be able to resist and absorb the impact. Then once the extreme weather clear slowly, the system should be able to respond and adapt with the new situation, new infrastructure. And then it should be able to restore the system so that some of the areas able to be supplied by electricity. This is like network reconfiguration, for example. Later we see one example about that. And after that, the system should be able to recover. So if you compare these two curves, the black one and red one, we can say that the black one, it is more resilient as compared to the red one. So from this graph, actually, we can see that resilience concept is considering the state changes according to the time. It's not only one state, but according to time. And most of the time, actually, resilience has been confused with reliability. Okay, if you know, like in power system, we have SIFI index, KID index. So there is a reliability index to measure how good is the system. However, resilience is different. And at the moment, there is no standard index to measure resilience. This is the difference between reliability and resilience. For example, in a reliability study, we look at the high probability, low impact event. This one is like N-1 contingency analysis. You remove one line, you run the analysis and see what happened. You remove one generator and see what happened. But in resilience, the event is low probability to happen, but the impact is very high. So this is the main difference between reliability and resilience. And resilience also concerned with the customer interruption time and the infrastructure recovery time, whereas in reliability it's more on the interruption time. They don't consider how it recover, how long it recover, but resilience, they consider this. And how we can evaluate resilience, there are two ways. We can look at the qualitative perspective. We could look at the quantitative perspective. Qualitative perspective is more on the studying the readiness of the system, whereas quantitative, we measure how good is the system resilience level. And it can be using simulation-based method, it can be analytical method, it can be based on historical data as well. This is one example of resilience metric. Actually, there are many other examples depending on the detail of the metrics. For example, if you look here, this is from Panteli. They have two resilience curves. The black one here, infrastructure, and the dash one is operational. And this is the equation to measure the resilience. For example, if you look at the number one, rate of degradation, it measures how fast the system degrades from the steady state here. Okay, this is the equation. We will not go detail, don't worry. Okay, and if you look at one case study done by my student in this system, we see that in this system we simulate using Monte Carlo to simulate the event of wind speed. And this is the fragility curve for different classes of distribution poles. So you can see that different wind speed will cause different probability of failure of the pole. The pole is for transmission line. So we consider different cases. For example, no tie line. This is tie line. DG. And then 5 tie line. Okay, different. We consider different analysis, and we found out that, look at the case number 4, 5 tie lines and 3 DG in the system, it able to improve the resilience, this curve, the green one, case number 4. Whereas the other, it degrade is the degradation rate is very high, as compared to this one. So here, actually, it shows that by having distributed generation and tie line, there has a high flexibility for us to change when fault happen at different location due to extreme weather. Okay. And the resilience metrics can have different characteristics. We can have a simple or more complex or retrospective or forward-looking, depending on the needs of us. Maybe some of the matrices is suitable for us to use in network reconfiguration. Some of it is for needed for planning purposes. So it's depending on the purpose of what study that we want to do. It's not the same, so depending. And then we have a resilient matrix. Resilient framework, Resilient framework is a step for us to improve the power system resilience. So actually there are many resilience frameworks in literature. This is one of it. We recognize the threat, and then define the resilient matrix, choose methodology, and obtain the result. So this is one of example. This is another two example of resilient framework. At the moment, there is no standard framework. So different utility have their own practice, how they improve. But in general, we can see that the resilient framework, it should have a closed loop, meaning the system should be analyzed and continuously updated. The strength of the resilience, because we do not know when it will happen and what is the impact. So a lot of analysis need to be done and a lot of data need to be used. Yeah, this is another two framework. Okay. So how we can improve resilience? Actually, in general, there are two ways. Number one, by improving the grid to be stronger and bigger. This one is related to hardening of measure. Hardening measure means we strengthen, for example, we strengthen the transmission tower, or for example, another example, we make sure that the substation is safe from flood. For example, in UK, what they did, they construct a tower, they construct a wall to avoid substation from become flood. Yeah? So this is one example. This is more on the hardening measure. And another one is through making the grid to be more smarter. This one related to digitalization. Yeah? And then one of it is microgrids. I will go a little bit detail on the microgrids. This is all the techniques that can be done to improve the resilience of power system. However, if you look at the cost, if you want to hardening or reinforce the measure in terms of improving the strength of the tower, substation, the effectiveness is high, but the cost is high. In terms of cost is high. Whereas if you improve the operational measure, it is more affordable, the cost is low, but effectiveness is not so good. So the best way, we took the hybrid approach. We try to make it hardening, reinforce the system. At the same time, we try to make it more smarter. Okay, because if too smart, also not good, because the human will lose control on the system. So you need to compromise between these two. Okay? So let's see what is microgrid. So basically, microgrid is a generator located close by the customer site. For example, if you look at this is distribution system. So we have a feeder here. So at the housing area here, we have one microgrid. This is microgrid. It can be like wind farm. It can be solar power, for example. So this is microgrid. And this microgrid can be connected to the system, or it can be islanded, depending on the need. Okay. So what is the advantage of microgrid? There are a lot of advantage, and the final advantage, it improves the resilience. The reason because when you have microgrid, the generation is close at the customer site, so it's much more easy to maintain, much more easy to look after. And microgrid also have advantage in terms of generate revenues. Last time in Malaysia, when whoever want to install their photovoltaic, they will get a feed-in tariff. Last time, it's quite good, because like 1 kilowatt hour, TMB will pay more than RM1. But nowadays, no more feed-in tariff. It's more on the net energy metering. The difference between what we sell to TMB, what we use, is our bill. So this is the advantage of microgrid, and also minimize environmental impact due to the usage of renewable energy. So let's see a few examples that prove why microgrid can improve the resilience of power system. So there are 3 cases here that I took. Number 1, East Japan earthquake 2011, Superstorm Sandy 2012, and Atacama Desert in Chile. So this is in Japan. During the Great East Japan earthquake 2011, okay, a lot of area being destroyed due to the tsunami. The microgrid, this is the microgrid. The microgrid consists of different system here. Is photovoltaic, gas engine, and other things here. So when this happen, it's still able to survive the loads. The customer at that area, the surrounding area. At least teaching hospital and also rest of home for 2.5 days during the blackout. Okay. And then this is another microgrid in Ropingi Hills microgrid, 6 natural gas-fired turbine. During this disaster, it's still able to serve that area, okay, where the system, the microgrid is islanded. Islanded meaning it is disconnected from the main grid. Okay. This is another example in US, where the microgrid at the New York University able to able to supply New York and New Jersey, some of the area, at least College of New Jersey, New York University, Princeton University, Stony Brook University. So this is the importance of microgrid, the advantage of microgrid. Okay. This is the microgrid that was installed in Chile, Atacama Desert in Chile, for remote area where they have the photovoltaic, wind power, and diesel generator. So this system have survived 3 extreme events. Number 1, during the mud avalanche caused by a large water flow, inflow, and then earthquake and storm. So during this event, the people in this area, they still have power supply. So this shows that by having microgrid, it's really helped to improve the resilience of the system, at least at certain area. Okay? This is example of the work that have been conducted in my group. It's on the energy management for microgrid, consisting of fuel cell, photovoltaic, and battery energy storage. This is the objective of the work. We will not go detail. So, but this the work here come up with a new technique on RAM rate control approach. Whereas we can see that if we are using the normal technique, because during the photovoltaic operation, the power that being generated, it is having a lot of ripple. So the system should able to smooth it by injecting power from the battery. But the existing technique is not so effective because it causes the battery to continuously working. Okay, whereas by using the technique that have been proposed in this work, the battery only work at certain time only. So we can make sure the battery life goes long way as compared to if the battery switch on and off continuously. Yeah? And then the other work that have been conducted is like islanding detection, microgrid formation, islanding operation, and load shedding. A lot of work have been done related to microgrid. So when the grid here disconnected, this is distribution system, the system need to be islanded, and to make sure it continues working, some of the load need to be removed. So the question, which load to be removed? Okay? So it can be a research there. Okay, this is one of the work that have been done by my PhD student, islanding detection. This is very important because islanding detection, the one that I have talked earlier about the event that happened in UK, why the power plants trip off when there is a problem, lightning strike, because the power plant detect it as a loss of main. But actually it's not loss of main. But because during that time the voltage changed, the frequency changed, so it detected as if the grid is lost. So to protect the power plant, it will trip all the power plant. But so that the islanding detection technique is very important for us to know when actually the grid is lost. The problem, the challenge, when the power supply from the grid here is very small as compared to the power from the distributed generation. So it's very difficult to differentiate whether the grid stay connected or not. So this is one of the challenge. So in this work, my student already analyzed 16 different power system parameters to identify which one is the most significant that can be used to differentiate between islanding or non-islanding event. This is another work. So as I have taught earlier, when the system is islanded, this is the grid. When it's disconnected, the system here will have frequency will drop because the power imbalance happened in this area. The DJ not able to supply sufficient load. So what happen, we need to remove some of the load so that the frequency is increasing. It will recover back. So this is about load shedding. And this is another work that has been done about load shedding, but considering different voltage stability indexes. Okay. And this is the work about network reconfiguration. Okay, network reconfiguration. The idea here, what is the best position of opening switches in distribution system so that the power losses is minimum. And another work that has been done is on the switching. Switching, because we know from planning, this is the end point that we want to achieve, but the process to change the position of the switches also need to be considered, which is not been considered in detail in the previous work. So this is the step taken. So we need to find the best step to minimize the disturbance of the system. This is another work that has been done related to network reconfiguration. And by network reconfiguration, we can see that the voltage profile is improved significantly as compared without network reconfiguration. Okay, actually there are a lot of work that can be done related to distribution system, related to microgrid. This is some of the work that's still available to be explored, like islanding detection, service restoration, network formation, a lot of others that can be explored. So I can summarize in different areas. For example, in microgrid area, we can look at the placement and sizing of distributed generation. We can look at the operation and control, because when microgrid is disconnected from the main supply, the control change. The decision to control the PV, the hydro, it will change totally. So it needs to be considered. Coordination during the microgrid, energy storage placement, sizing. And then other is like system configuration and protection. Because most of the time the protection is neglected. But actually in practical, we see that when changes happen due to extreme weather, protection need to be looked again. For example, the one that we have talked about the UK event last year, the protection setting need to be considered not only due to outages, but also due to the extreme weather. You need to be relook again. So this is some of the work that can be done, still can be explored. So also we can look at the communication and monitoring, IoT, cloud computing, SCADA, big data, data mining. And then we look at the modeling catastrophic events, because we need to know how the storm behave, how the flood behave, and which area. So it can involve geographic area as well. So a lot of things actually can be explored from the civil perspective, from mechanical, how to make the more strong substation to avoid flood and others. So a lot of things. Let's see one example. By example, so let's say if you have a system here, this is a distribution system, and this system having open switch. This is the open point. This is not connected. But when fault happen here, okay, we can isolate these 2 points so that we can isolate the fault, and we can connect this line so that it can still survive. We minimize the impact of unserved customer. Let's say if you have hurricane, start from here, moving here, so the system will be, some of the line here will be destroyed. So the system should be able to isolate, to react fast, so that this area can be one microgrid area, this is another microgrid area, this is another area. So we just isolate the system, the faulted area as only. The rest should be able to operate. This is how we can improve the resilience. And a lot of research can be done in this area, like how we can manage the algorithm to on and switch off the point here optimally. We can look at the control and stability. Different area can be explored. As I said, when the system disconnected, the control need to be changed. It will not be the same when it connected to the grid. It will change, totally change, and this one need to be considered. Okay, for example, one of the major problem now is about the inertia of the system. Because the penetration of renewable energy nowadays is too high, what happened, the total inertia is become very low. So small disturbance will cause a large problems because the inertia can help in terms of maintaining the frequency of the system. So there's an area called it virtual synchronous generator area. So this one also can be explored. And from the perspective of communication, it's a data mining, monitoring, so the system should be able to very reliable data communication so that we can gather a lot of data, we can do a lot of activities during the extreme weather. Okay. And other research that can be considered like definition. There is no standard definition at the moment about resilience. Framework also no standard definition. So if we have these two, it will help the power engineering area a lot. And then the matrices also not no standard resilient matrices as well. And we need to look at the different matrices because different purpose need to have different metrics. It's not one metric can suit all the problems, to solve all problems. So this is also area that can be considered. So I would like to conclude my presentation today. So we have seen from my presentation today that the frequency and intensity of extreme weather is increasing every year. And it occur a lot of damages to human as well to the infrastructure or power system. And as we know, power system is critical infrastructure, so that it is very important for us, for power engineer, for researchers to find a way to improve the strength of the power system, to improve the resilience of power system. And the best way at the moment is to look at the distribution system, because distribution system is the most area that being affected by extreme weather. For example, flood, it caused submerge the substation a lot. So this is the best way to tackle, to improve the resilience, to strengthen the system. And then when we improve the resilience of the system, actually we improve overall performance of the system, not only during extreme weather, but actually during the normal operation, the system also become better. And the need of improving power system resilience actually is open a lot of area as well, not only in power system or electrical, but it also open new area in mathematics, geography, computer science, civil engineering, and others. It's more on the hardening part, it's more on the civil or mechanical area. So a lot of work can be done in this area. All right. So I would like to acknowledge, this is the end of my presentation. I would like to acknowledge my teachers, primary school, secondary school, and also a lecturer in electrical engineering department. Prof. Kaha, also my lecturer. Who else? Prof. Saad actually was my tutor when I was a student here. Prof. Hamza. There are few still in our department. Thank you very much for train me to be an engineer. I would like to acknowledge the top management, Fakulti Engineering, for the support and funding so far given to me. Actually, it really helped me a lot to progress in my work. I really appreciate that, especially the high impact research grant. It really helped me to be better. And then I would like to acknowledge industrial partner, TMB, ILSAS, who have given me a lot of idea to work in more practical activities, more practical research instead of just theory work. And my past and current student, I have learned a lot from my student. And actually, to be frank, like this resilience also, I learned from my student where they give more idea to me to explore in this area. Thank you so much. My mentor, colleagues and friends who helped me a lot. I'm really blessed with surrounding by very excellent friends in the department, in the faculty that helped me a lot. morally, indirectly or directly, to help me to be better person. And my family member, my mother, my wife, my children who always support me, understand sometimes I brought work at home until midnight. So what to do, because sometimes a lot of work, the deadline, need to read student paper, so we need to do that. So thank you very much for understanding myself, and may Allah bless all of you, great reward in this world and hereafter for your kindness. And thank you very much for all the audience today. Thank you very much.
Thank you, Prof. Hazlie Mokhlis, for the inspiring lecture. Now, I would like to invite Professor Rofina Yasmin to conclude the lecture, which has been delivered by Professor Engineer Dr. Hazlie Mokhlis. Please welcome.
Thank you very much. Thank you, Professor Dr. Engineer Dr. Hazlie Mokhlis, for the amazing lecture. Actually, I thought I was going to be totally lost, but this topic, I think, is something that affects all of us. And I don't know whether you're, I think he's very young, but do you remember 1997, the national total blackout, right? And just a few hours, the whole country was without electricity, and all of us thought, wow, it's almost like the end of the world. We cannot function without power. Nothing works. So this concept of resilience and readiness is, I think, resounds with all of us, and I think we cannot. We're very proud that is very much a part of doing research in this very important area of power resilience. So. As I said again, although I'm a biologist, a microbiologist, we have a similar concept. We have this readiness, HACCP. I don't know whether you know the risk assessment and readiness. And again, in this world that we live in, our activity is dependent on many things, including electrical energy. So the topic presented here is definitely very timely. When we talk about climate change, we talk about the increase in the strange weather patterns across the world. There's a volcano about to erupt in the Philippines, and we are quite sure that will cause disruption in power systems as well. So, I really like the idea of having an island microgrid. I hope will take the lead and maybe start to create a model microgrid for our area here. We've had blackouts so quite often due to this central grid. So, it's something, I think Prof. Saad said that this is a real possibility that may take the lead in creating the first microgrid in the university and can serve the university and as well as its surrounding communities in terms of need. So I believe the research conducted by Prof. Hazlie is in line with the university's strategy in cultivating high-impact research. And I'm really glad to see the transition between fundamental research into applied and experimental research and research that totally impacts the industry. And very much because of the collaboration that Hazlie has with industry, I think that's a very important link that we want to cultivate and encourage our partners in industry. Will really bring us, put our feet on the ground, so to speak, in terms of what the country really needs. And I believe the research that he does here will transcend beyond just writing papers and patents, but will impact not only just the industry, but the nation's readiness, kesiapsagaan negara, they say, or our readiness in terms of disasters. And I would love for and engineering to be more involved in policy, for instance, in maybe auditing Malaysia's readiness for disasters in power energy, and in creating new maybe policies or even regulations, and definitely for standards. For creating new standards for the country. So I think we need to move into that space as the top university in Malaysia, to not just be known for our academic excellence, but to be known as well as contributing to the national agenda as well. And I think this is a really great opportunity in terms of this research. So, and I love that in the last slide, you talk about interdisciplinary collaboration with other disciplines like IT, mathematics, science, geography. Don't forget economics, because the forecasting of disaster is an economic issue that we have to incorporate into our budget, national budget, and national planning. And it's not there, you know. I mean, if you look at budget 2020, if you look the funding for readiness for natural disaster, I think it's quite minimal. It's always on just flood, but not on the consequences of flood, like power and things like that. So, you know, this is something everybody, I think we have the talent, we have the capacity, and, you know, we have the support to really be a big player in this space. So I really congratulate Professor Engineer Dr. Hazlie Mokhlis for his wonderful research and very clarity of his talk. And I'd like to invite everybody to join me again to give a big round of applause. So thank you very much. Wassalamualaikum warahmatullahi wabarakatuh. Thank you everyone for being here with us today.
Thank you, Professor Rufina Yasmin, for chairing this inaugural lecture. With this, we have reached the end of the inaugural lecture. Now, I would like to request everyone to stand up for the University of Malaya song to close this event. Please rise. Thank you. Please be seated. On behalf of University of Malaya, I would like to thank the management of Faculty of Engineering in organizing this inaugural lecture and all distinguished guests for your presence. Lastly, we will proceed with the photo session. So everyone please be seated for the photo session. And as for now, I would like to invite all guests to proceed to the lobby area for some refreshment. Once again, thank you and have a pleasant afternoon.